Hello, and welcome to this topic, the moving sofa problem. We discussed a problem about the length of the longest thin rod that can carry it around the corner last time. Today we are going to move from the length to the area, the moving sofa problem. The mathematician Leo Moser posed in 1966 the following curious mathematical problem. What is the shape of the largest area in the plane that can be moved around the right-angled corner in the two-dimensional hallway of Willis 1? This question became known as the moving sofa problem and is still unsolved more than 50 years after it was first asked. The latest development is from mathematician Dan Romick. The following introduction and pictures are from his homepage, so this homepage. And if you want to learn more about the mathematics of moving sofas, please read his paper and the other references cited at the end of this section. Now, suppose this is the right-angled corner in a two-dimensional hallway of Willis 1. And let's think, what kind of sofa shape we can construct that can move around the corner? What is the shape of the largest area that can be moved around it? Please think about it. Emily, do you have an idea?
I think the unit square will work.
Thank you so much. Yes, very good. Now let's try it. So this is the unit square. Move upward. Then turn to the right. All right, perfect. Where we know that a unit square only has area 1. Can we do better? Jack, what do you think?
Why don't we try some circles? How about the semicircle?
Good idea. Let's see if it works. So let's try it. This is the hallway. This is the semicircle. So this semicircle move upward. At this corner, it rotate. Then move. Yeah, very good. It works. Terrific. We can see that the semicircular sofa has a larger area than the square one. And could you find the area? Because the radius is 1, so the area is pi over 2. It's approximately equal to 1.57. It's greater than 1. Yes. It is also more interesting because in order to move around the corner, it rotates. Whereas the square sofa merely translates. Now, if only we could combine rotation and translation, maybe we could construct an even bigger sofa shape. Indeed, the mathematician John Hammersley noticed that if the semicircle is cut into 2 quarter circles, which are pulled apart, and the gap between them filled with rectangular block, then we get a larger sofa shape, which could be moved around the corner if only a smaller semicircular hole is also removed from the rectangular block. Here is the resulting shape. That is starting to look a bit more like an actual sofa. Hammersley's idea works for every value between 0 and 1 of the radius of the semicircular hole at the bottom. The shape of a maximal area in this family is obtained when the radius is chosen to be 2 over pi, approximately equal to 0.637, which gives area of 2 over pi plus pi over 2, or approximately 2.2074. This is much better than the area of our simplest sofa, the unit square, this one. And Hammersley thought his construction may be optimal, but this turned out to be false. In 1992, Joseph Gerver found a better shape with a slightly bigger area of around 2.2195. Here it is. Gerver did not prove that his construction is optimal, but it was derived from considerations of local optimality. Roughly speaking, the area of the shape is in equilibrium when making small perturbations to the path through which the shape is transported to move it around the corner. This leads to differential equations that can be solved to find formulas for the different pieces of the shape. There are 3 straight line segments and 15 curved pieces, and each described by its own formula. Thus, it seems quite plausible that Gerver's shape could be the correct solution. Gerver conjectured that it is, and it remains the best one known today. The moving sofa problem has several other variants. One of them, studied by John Hutton Conway and others, asked for the largest area sofa that can be moved around a 90-degree turn both to the right and to the left. By extending the techniques used by Gerver in his 1992 paper, Dan Romeich found such an ambidextrous sofa shape with area of approximately 1.64495, which may be the largest possible area. Here it is. Similar looking shape were computed numerically using approximation schemes developed by Kiyoshi Maruyama in 1973 and Philip Gibbs in 2014. Romeich's derivation used a solution in closed form for the shape. It has 18 distinct pieces, each of which is given by a separate formula obtained as a solution of some differential equation. The details of the analysis are quite surprising. For example, it turns out that the area of the new shape is given by the Euro formula, like this one. 50 years after its inception, the moving sofa problem continues to lead to new mathematical insights and nice-looking pictures and animations. That's all for this section. Hope you enjoy it. Thank you.